Welcome to this lecture on non-native structures. My name is Raj Pala. I am a faculty at the Indian Institute of Technology at Kanpur. At the outset, I would like to thank the organizers of the conference, International Symposium on Modeling of Crystal Growth Processes and Devices, especially Dr. M. Srinivasan. The talk is divided into three broad themes. First, I would define what is meant by non-native structures. Then we will address the issue of why such a definition is productive in the design of certain electrochemical materials, why we need these materials. Then the third theme would be how do we go about synthesizing them, assembling such materials. Much of what I'm going to talk is elaborated in these two review articles. This review article was written with my collaborators, Sulai Saha and Prashant Gupta. Much of this work would not have been possible without the productive collaboration with many faculties at IIT Kanpur, especially Professor Shivakumar in the Chemical Engineering Department, Professor Anna Subramaniam in Material Science Engineering Department, who is also giving a talk in the symposium, Jishnu in the Mechanical Engineering Department, and Kalod in the Material Science Engineering Department. Many students have collaborated with me in this area. These two students are also co-authors of this review article. And we've been pursuing this theme for almost close to a decade. So a lot of students have been involved in this work. I also acknowledge the funding from the Department of Science and Technology and Indian Space Research Organization. Like most of the contributions here, this contribution also addresses an important area of research, which is sustainable energy and environment, specifically how to utilize solar energy, how to convert solar energy and store solar energy. We are more focused on electrochemical approaches to solar energy. We have also worked on some aspect of how to utilize hybrid inorganic organic perovskites to capture solar energy, but we have done a lot more work on batteries, which is an important aspect of solar energy conversion and solar energy storage. There is a direct approach of converting solar energy to chemicals, specifically hydrogen, which can further be utilized for generating electrical energy via fuel cell. We have worked a lot in this area of photoelectrochemical conversion. It's a grand challenge problem in chemical science and engineering. There is another approach to generating hydrogen. You can capture solar energy using solar cells, use that electrical power so generated to run an electrolyzer, let's say water, split water into hydrogen and oxygen, and generate the chemical fuel. The hydrogen so generated can also be utilized for running an internal combustion engine to generate mechanical power. So we consider hydrogen to be a central solution to this issue of sustainable energy. And the other approach to sustainable energy via electrochemical means is the batteries. There are three aspects to our research. So all these three are closely coupled. So we develop materials, we undertake measurements, and we also model the measurements so undertaken. So there is a particular theme in the way we do things. We try to develop fairly simple models and utilize sustainable materials. So this is a graph which is very useful for the design of sustainable materials. So this on the y-axis, the abundance of materials, on the x-axis, the atomic number. So typically, large area devices are going to be assembled using materials in this regime. So these are precious materials. If there's a large area device involving these materials, these are going to be replaced by materials from this regime. We also develop instrumentation. Sometimes we have to develop our own instrumentation to explore certain kinds of properties. That's another theme of our research. So materials, measurements, and models are the three themes which we undertake. So to go to the first part on what you mean by non-native structures, we contrast this non-native structure with the native structure. Native structure is the bulk structure, the most stable bulk structure. When you say bulk, there is no influence of surface. So this definition is sort of inspired from what is used in biological systems, proteins, for example. So native structure refers to the most stable bulk structure, and a non-native structure differs from the bulk structure in terms of discrete translation symmetry. Okay, so this is entirely a structural definition. So here I show the bulk structure of CDAC. It has a word-side structure. As opposed to this structure, this is the rock salt structure of CDAC. This has been stabilized. CDAC has been stabilized in the rock salt structure by certain procedures. That's not important. But all I want to emphasize here is the definition of non-native structure. That is, it has a different discrete translation symmetry from the bulk structure. For this system, we had analyzed the reasons for the stability in the non-native structure, utilizing computational means. We had looked at the interfacial energies involved in the pseudomorphic stabilization of CDAC in the rock salt structure, the mechanical stresses involved, and we had provided thermodynamic criteria on when CDAC can be stabilized in the rock salt structure as opposed to the bulk word-side structure. We had generalized these themes for a variety of systems, and some such systems are provided in these two publications. We had adopted a new nomenclature of non-native structures due to certain reasons. This issue of polymorphic metastability is not that straightforward. Okay? It's not very easy to determine when a structure is metastable, especially since the stability and metastability is a size-dependent property. What is metastable in a particular size regime can be the stable structure when you decrease the size of the crystal. Okay, so we wanted to avoid these kinds of definitions, even though they have their own power. So we adopted an entirely a structural definition based on discrete translation symmetry. But we had adopted a certain nomenclature which are indicative of stability. For example, if you take MnO2, MnO2 is a dream system for this kind of an approach because it has a variety of non-native structures. Let us go through certain nuances of this nomenclature. For example, the traditional nomenclature, pyrolusite, beta, and so on, doesn't really provide indicators of stability. Here, we are using N to indicate native structure, that is the most stable bulk structure. And there are other structures which are called Ramstellite and so on. These conventional names do not provide an indicator towards the thermodynamic stability. Here we are referring to this structure as non-native 1. And this is non-native 2. This is an intergrowth structure between native structure and non-native 1. You can have non-native 3, which is even higher energy structure. These are very important because they are layered structures. They can be delithiated spinel structures, which are referred to as non-native 4. So these are also going to be important in defining heterostructures. These are isomaterial heterostructures. What do we mean by isomaterial? It is just the same MnO2 in two different structures between, here in this case, native and non-native structure. Okay, so this new nomenclature has certain utilities which we have elaborated, for example, in this manuscript. With that completes the section on what we mean by non-native structure. So we move on to the next theme on why non-native structures are important. Here we give a schematic illustration to the working principles behind a lithium-ion battery. So in the charged state, lithium is the anode, for example. Lithium ions are graphite, intercalated into graphite. As lithium ions as the battery gets discharged, the lithium ions are translocated across the electrolyte and intercalate or bind to the cathode structures, materials of the cathode structures. These cathode structures are typically transition metal oxide structures. So as the battery gets discharged, the voltage gets decreased. So for example, one of the cathode structure can be lithium cobalt oxide. As the battery gets discharged, lithium cobalt oxide gets formed and lithium ions gets transformed from this structure at the anode. The anode gets delithiated and it forms graphite. The anode becomes graphite, delithiated graphite. So the opposite reaction occurs during the charging of the battery. We have identified contravarying properties which are critical in the efficiency of lithium-ion batteries. We will elaborate what I mean by that. So for example, the energy density depends upon the capacity times the voltage that you can obtain from a lithium-ion battery. The potential that you can obtain from a lithium-ion battery is dependent upon delta G of intercalation of lithium ion with the cathode of the lithium ion battery. The greater is the delta G, that is, I want to clarify, by greater I mean more negative energy, because to get voltage of the battery, you want to undertake an exothermic reaction. If the exothermicity is more negative, you can get greater voltage from the lithium-ion battery. So typically, if you have more open structures, you can get greater voltages from the battery. And the kinetics of intercalation, deintercalation is more facile, it's faster, but because of it being a more open structure, the stability is lesser. So these two properties are contravariant with stability. If you get greater voltage, more facile kinetics, you get lesser stability. Let's go to another system, another electrochemical system, which is photocatalysis. Same things are applicable for photoelectrochemical catalysis. So there are three fundamental physicochemical events. First, there is photon absorption, which depends upon the band gap of the material. Once the photon has been absorbed, an electron-hole pair is being generated. Then this exciton has to be separated and moved apart in different direction to undertake surface electrochemical reaction. The holes are involved in oxidation reaction. The electrons are involved in surface reduction reaction. So these three events are important in the efficiency of photocatalysis. Photon absorption, exciton generation and separation, and surface electrochemistry. This is a holy grail problem in chemical science and engineering. A lot of efforts have been, a lot of ideas have been undertaken to improve the efficiency of these materials. Again, we can identify contravarying and covarying properties. Here, contravarying properties are the greater the therm band gap, the thermodynamic driving force for photoelectrochemical reactions are, the thermodynamic driving force is higher, but the photocurrent is lesser. There are certain approaches that improve the optical absorption, but that typically decreases the efficiency of electron-hole separation. So again, these are contravarying properties. If you try to do this better, you typically end up hurting this process. All these issues are elaborated in this article. Moving on to the third system, which is, let's say, oxygen evolution reaction, which is important in electrolyzer. Electrolyzer involves two electrochemical reaction, oxygen evolution reaction, hydrogen evolution reaction. For a rational design of these electrocatalysts, we typically look at the Volcano plot introduced by Trisati many years ago. Typically, there are two legs of a volcano determined by certain events which are limiting absorption. Sometimes in this leg, certain desorption is being limited. Okay, so again, if you're not familiar with this, please look at this manuscript. So such design principles have been utilized for looking at electrocatalysts, especially oxygen evolution reaction and hydrogen evolution reaction that is important in the design of an electrolysis unit. So again, we can identify contra and covarying properties. Typically, materials that are very active are less stable. If you try to improve activity, they become less stable. If you improve the stability, conductivity of the material decreases, the electrochemical surface area decreases. So these are contravarying properties, and there are certain scaling relationships introduced by Jens Norsko's group, which relate to covarying properties. Typically, these are the energies of reaction intermediates are related in a covarying manner. that also limit the extent to which the efficiency of electrocatalysis can be improved. To go beyond the contra and covarying properties, we argue more elaborately in this manuscript that it is important to modulate the bulk coordination and form heterostructures. Okay? So bulk coordination typically control the band gap, ion intercalation, diffusion of ions in the bulk. If you can modulate the bulk coordination, you can change all these properties. If you can change the surface coordination, the trends in electrocatalysis can be improved. And the coordination at the interface is going to be important in band alignment between the conduction band and valence band at either side of the interface. This again will in turn control the electron-hole separation. So why are we referring to these properties? These are the properties that are going to be determining your efficiency of lithium-ion batteries, the electrodes involved in lithium-ion batteries, in electrocatalysis, as well as in photoelectrochemical systems. We'll get back to our central approach for designing these material devices, which is using non-native structures. So the native structure, as I had mentioned, it is determined by the bulk ground state material. These are thermodynamically stable materials. These are typically more easy to synthesize compared to non-native structures. These are the non-native structures. These are harder to synthesize. They're less stable compared to the native structure. In this case, I'm showing the structures involved in the non-native structures of MnO2. Supposing you are able to synthesize the non-native phase of, for example, in this case, MnO2, because they are higher in structure, higher in energy, you can, when you heat the structures, they naturally will get converted to the native phase. You can modulate this thermal transition and arrest the transition in between before the complete conversion to the non-native phase. And that is an approach to forming a heterostructure. Using such a heterostructure, we can we have improved the cathodes of a lithium-ion battery. Here we show two important aspects, rather three important aspects: higher voltages, wider voltage plateau, and higher capacities. Here we are showing the native structure. Then we can modulate the intergrowth structure, that is a native, non-native structure, and there is a complete non-native phase. So by modulating between these three regimes, that is from the native structure to a non-native structure and native, non-native structures in between, we can improve the voltage and we can increase the voltage plateau. That is, I'm plotting the voltage in the y-axis. This is a measure of the extent to which the battery has been discharged. We can also improve the capacity using this approach. The emphasis here is that if you can control the native and non-native structures, you can improve all the critical features of the cathode involved in lithium-ion battery. Specifically, we demonstrated this using MnO2. So as I said, MnO2 has different structures. The non-native structures are more open structures. Therefore, when lithium-ion binds to the non-native structure, the delta G will be more negative, because of which you can get greater voltage. Because they are more open structures, you can get faster charge and discharge kinetics. And if you can make an interface between native structure and non-native structure, you can also stabilize them to a greater extent. All these things was demonstrated experimentally and modeled computationally using density functional theory. These results are elaborated in these two publications. So what is the trade-off here? Again, this is the trade-off is related to contravarying and covarying properties. If you want to improve the voltage, you're going to make compromise on the stability. So to get optimal voltage behavior as well as stability, you have to form an interface between native and non-native structure. The optimal structures are often the heterostructures. That can be rationalized by arguments based on the properties of the individual native structure and non-native structure. Moving on to photoelectrochemical systems, we can modulate the electron-hole separation using the native structure and the non-native structures, which have different band edges. And you can assemble heterostructures in different manner. For example, bicompartmental quantum dot heterostructure is shown here, assembled between CDSC and ZNS. This bicompartmental quantum dot have very high exciton lifetime. So here we show a heterostructure formed between the native structure of TiO2, which is the rutile structure. Here we show the non-native structure of TiO2, which is the anatase structure. Because of the staggered band alignment between the native structure and the non-native structure, there is an innate driving force for the holes to move in this direction and to electrons to move in this direction. So again, this has been more elaborately explored in an exhaustive study mentioned here. So these heterostructures between native and non-native structures have different band gaps and different band alignments. Depending upon the interfacial structure, the efficiency of electron hole separation is very different. So if you take variety of heterostructures, there are lots of possibilities. We explored all these heterostructures in terms of band gap, in terms of band alignment, and interfacial strain that exists between the native and non-native structures. And we were able to, based on computational study, we were able to come up with what would be the optimal interface formed between native phase and non-native phase. So this is an exhaustive study involving a variety of native structures and non-native structures involving ZNO, TiO2, bismuth vanadate, CDSC, and ZNS. So we were able to come up with what kind of combination would give you an optimal type 2 heterostructure, type 1 heterostructures, and so on. Moving on, again, this kind of philosophy involving forming an interface between native and non-native interface was utilized for forming oxygen evolution electrocatalysts. Again, this is for MnO2. So different structures were explored both experimentally and computationally. And we were able to rationalize why a particular structure is the optimal oxygen evolution electrocatalyst. This, again, the optimal structure can be rationalized using the properties of different non-native structures and native structure. Again, this approach has been demonstrated for a variety of, using variety of systems. In this case, we are using ruthenium oxide, which is a very powerful oxide for oxygen evolution reaction. We improved upon the properties of ruthenium oxide and modulated using support effect and scale to the peak of Volcano. That is, we improved the activity by forming better interfaces. This is elaborated in this manuscript. We have extended this approach to a variety of other systems also. For example, in this manuscript, we utilize a similar approach involving bulk metallic glasses and design hydrogen evolution electrocatalyst. So with that, we conclude the theme on why non-native structures are important for the design of lithium-ion battery materials, photoelectrocatalysts, and oxygen evolution electrocatalysts in general. Moving on, we'll address the final theme of this lecture on how we have tried to synthesize and stabilize the non-native structures. This issue of metastability and stability is a delicate issue. A lot more discussion is required to really calibrate which is metastable and stable. We'll just broadly mention different approaches we have utilized in this. We have utilized, let's say, to stabilize the non-native structure, we have stabilized them using, let's say, pressure and so on. In this case, we show lanthanum vanadate, which we stabilize using pressure and temperature and using certain ions. In this case, europium ion, to stabilize the different non-native phases of lanthanum vanadate. This is important for optoelectronic applications. This elaborated in this manuscript. We also looked at regimes wherein these metastable structures are stable. For example, in this case, europium-doped magnesium oxide was analyzed, and we identified temperatures and dopant concentration wherein we can metastabilize these structures. Okay, this is elaborated in this manuscript. So, an important theme in this area is how do you form heterostructures? We have typically utilized two approaches. One is supposing we are able to form a non-native structure, we can thermally phase transform that non-native structure to native structure. But if you can arrest the phase transformation, we can form a native and non-native interface. We have utilized this for a variety of structures to form different kinds of heterostructures. These are elaborated in this manuscript. We have also analyzed this exhaustively in the case of TaO2 and using certain molecular simulation techniques, and also compared the heterostructures that we obtain from computations with those obtained in experiments. And a powerful approach for assembling a native and non-native structures, heterostructures, is the click chemistry. We have demonstrated this for a variety of technique, a variety of system. This is a very, very important system. We have addressed this in a variety of electrochemical contexts. Photoelectrochemical context is a very stable approach to forming a non-native and a native heterostructure. This was first introduced in this manuscript long time ago, and we have extended this approach to a variety of systems. To summarize on how we can stabilize and form interfaces with non-native structures. We have utilized variety of solvents and ligands to stabilize non-native structures. We have utilized pressure, and we have rationalized why pressures are going to be important in stabilizing non-native structures. We have also utilized rapid temperature quench for generating bulk metallic structures. We have also utilized that for hydrogen evolution reactions. We have utilized pseudomorphic growth for stabilizing non-native structures. We have also, in some cases, explored the phase diagram involved in doped metastable structures. This has been a powerful approach, click chemistry, to generate an interface between non-native structure and native structure. We have also demonstrated how do you generate heterostructures using thermal phase transitions. The last theme we'll just wrap up in a few minutes, which is we've explored the growth of non-native structures. There are many important questions, okay? What determines the crystallite size in a nanoparticle? How do you visualize these structures in early stages of crystal growth? Because these are involves very fast time scales. It's very hard to visualize these things, structures. But what we have seen is that this a detailed slide. I'll just take a minute to elaborate what we have shown here. What we see here is that when a native structure is formed, before the formation of the native state, there are a lot of precursor states. For example, the precursor state can be just a precursor itself. For example, in this case, let's say you are involved in the formation of, let's say, lanthanum fluoride. You assemble lanthanum fluoride using different precursors. And then first you form an amorphous structure. That is a non-native structure because it has a different discrete translation symmetry from the native structure. And then this amorphous structure is transformed into a non-native crystalline structure that is formed within the amorphous structure. And within this non-native crystal structure is formed a native crystal structure which continues to grow and form a larger native structure. What we saw experimentally was that as the crystal structure is getting transformed from the most non-native structure to native structure, during this crystal structure, there's a size reduction. Okay, so this seems to be sort of paradoxical, right? As the crystal growth occurs, there's a size reduction. Okay, this is what we observed. We are very excited about this result. We visualize these results using 3 techniques, using PL lifetime, wherein we saw during crystal growth there is a size reduction. We calibrated this using XRD as well as HRTEM. So they're using these 3 different techniques. There is a lot of circumstantial evidence to suggest that when the crystal growth occurs, there is a phase wherein there is size reduction. Because of certain features involving mechanical stresses that are generated during phase transformation, we developed a model. This is an evolving model. A lot more work has to be done, but we developed a first generation model involving finite element analysis of mechanical stresses, and we were able to come up with a phase map involving 3 parameters. Okay, one involving misfit strain between different native and non-native phases. This axis is a measure of fracture toughness, and this line is a measure of inherent defects involved in the crystal. Based on this, we were able to come up with a phase map on wherein phase map to suggest where you may see this size reducing crystal growth and where you may not see. Okay, so again, I'll emphasize this is just first generation model. Lot more work has to be done for lot more system to really understand why there is a size reduction during crystal growth. Just to conclude, we have tried to address three parts. First is what are non-native structures? These are non-native structures involve different discrete translation symmetry compared to the bulk, most stable bulk structure, that is the native structure. These have non-native structures have different discrete translation symmetry. We identified contra and covarying properties in lithium ion batteries, photoelectrochemical system, oxygen evolution reaction that limits the efficiency, and we argue that non-native structures and heterostructures formed between native structures and non-native structures will help us go beyond these limiting behaviors. We are trying to design these non-native structures and interfaces using a variety of design principles, thermodynamic design principles, kinetic design principles, structural principles using space group theory. Lastly, there is a particular feature of crystal growth involving non-native structures, wherein we see size reduction during crystal growth. This is a very paradoxical term, size reduction during crystal growth. We are very excited, but a lot more work has to be done in this area to nail down the underlying physics seen in these systems. I've taken a few more minutes than what was allotted. I apologize for that. I welcome questions on what was discussed in this talk. Thank you.